I'm Guy Backstrom. I'm the director of the United States Department of Energy Radiological and Environmental Sciences Laboratory, otherwise known as RESL, not RESL, but Russell. Don't ask me why, but so today I kind of want to just talk about the reference materials or those isotopic standards that we need from the NMIs. Um, from a reference material producer's perspective that we actually use to produce real world reference materials. So I'm calling this RM cubed. So who is Russell? So we're really a United States federal metrology laboratory specializing in radiological reference material, right? And our main mission is for the United States Department of Energy, but we're also a reference laboratory for the Nuclear Regulatory Commission, and the Air Force, Navy, and some other federal agencies that we work with. And our main thing is we provide performance testing or reference materials to evaluate analytical results that agencies use to make these important decisions, right? Especially for the environment, worker protection, or even the general public. Our main programs at Russell is one of them, we have what's called the Department of Energy Laboratory Accreditation Program, otherwise known as DOLAP. And for example, in 2022, we coordinated the accreditation of 23 dosimetry and radiobioassay programs throughout the Department of Energy. These programs monitor over 75,000 Department of Energy radiation workers and make approximately 180,000 measurements per year. Radiobioassay measurements are on the order of 30,000. The other 150,000 are really dosimetry, from the TLD badges or the OSL badges. Russell also, besides being chemistry, we also have an irradiation facility where we're irradiating dosimeters. So we test all that kind of stuff as well. Another one program that we have is called the Mixed Analyte Performance Evaluation Program. In this program, we're testing water, soil, vegetation, air filters. My non-favorite gross alpha beta air filters and waters, but everybody does it, so they want that. And we essentially in 2022, we made approximately 1,600 samples, evaluated over 5,000 results that essentially led to issuing 60 letters of concern to various stakeholders, letting them know, that their laboratories were having problems. And within the United States, we're testing essentially 90 domestic laboratories that do radiometric type of measurements, and international, there's approximately 40 international laboratories throughout the world that participate in this program as well. This is a free program, so anybody except, there's a couple of nations the United States doesn't like that can't play with us. But anyway, are welcome to play in this program. Unfortunately, if you're an international laboratory, we do have to charge a very minimal shipping charge. So if anybody's interested, you can contact me, whatever, we can get you into it. We also have what we call a site-specific performance evaluation program. And so really mostly for our Department of Energy customers, but also other agencies, we will make custom-made radiological testing items, to support those really unique radiological missions. What allows us to do this? So this is our pedigree, if you will. Our first thing is we have a two-way exchange with NIST, our NMI, and this two-way exchange is we make standards, send them to NIST to analyze, and then NIST makes us standards in all of the matrices that we mostly make, and test us blind to ensure that we have the measurement capability, that analytical capability to do the work that we're claiming. Then we also open ourselves up to accreditation through the American Association of Laboratory Accreditation, which is called A2LA. And we follow the various ISO guidelines, 17025, for example. I think everybody's familiar with that. 17043, so that's the general requirements for proficiency testing provider. And then, of course, 17034, because almost everything you make for proficiency testing is a reference material. So we go the one step farther and, get credit to be a certified reference material producer. So across the United States, I don't know if you can see my cursor. Here's Idaho, if anybody's interested. It's a sweltering -3 degrees Fahrenheit or -20 degrees Celsius here this morning. And this is the whole reason why the United States never joined the metric system, right? Because -3 degrees seems a heck of a lot warmer than -20 degrees Celsius, right? But anyway, so across the United States, these are various sites that we're keeping an eye on that the Department of Energy has. So what are our needs from the NMIs, right? Well, really what's driving this is because, ICP mass specs, have really come down in price over the last 10 years, right? And so right now we're on this about the same order of magnitude of cost of what a rack of alpha spectrometers cost, right? So, around $150,000 to $200,000, you can get a mass spec versus, a rack of alpha spectrometers with about 30 detectors in it. And so, that's kind of what's driving this, because we all know, if we can couple the separation chemistries that were necessary for those actinide measurements with the accuracy and speed of the mass spec, we're going to have these way better measurements, right? And so, for example, just an example is, mass spec, we can easily hit uncertainties on the order of, 1% versus alpha spectrometers. You're limited to uncertainties to around 3 to 5%, right? And so, anyway, that's this whole cost thing for the instrumentation is really what's driving our needs, right? Because more and more laboratories that I work with are switching over to mass spec. So what do we need? Well, and hopefully Richard, you get this, right? And so standardize and accurately determine the minor constituents in these standards, right? So if it's a 99% pure plutonium-240 standard, well, how much that should be 241, 236, 238, 239, how much of those are actually in it with some definite, known amounts, right? Because what I like to do is I like to take, these very pure plutonium-239 standards, the pure 240 standards, mix them together to make different isotopic ratios that then we test laboratories with, right? So if I have a 240 standard, I need to know how much 239 is in it so that when I take my other 239 standard, I can mix them together and and have a very accurate number that's reliable, right? And really some of the activities that's going on, of course, I think this is pretty common around the world, is, fuel reprocessing, decommissioning, the norm that's coming from the, oil exploration type of stuff, legacy management of our waste, and then, of course, one of the big drivers is the non-proliferation efforts, right? And so these are just some of the isotopes we're looking at: thorium-232, neptunium, the uranium series, the plutonium series, and then of course americium, right? In the waste decommissioning world, radium-226, again, a lot of that comes from the oil exploration world. And then lanthanides, okay, the radioactive lanthanides. This may not be for mass spec per se, but when we're decommissioning and you have those biological shields, hopefully folks know that in mass spec, right, you're always seeing the lanthanides. They're everywhere in the world. And so what's happening is, those pesky little neutrons are hitting the natural occurring europiums, for example, and causing, them to go radioactive. So, for example, europium-151 of natural abundance of 48%, gets converted into europium-152, which, is a fairly long half-life, right? So anyway, things like that we're looking at. And then decommissioning or long-term waste monitoring, iodine-129, tech-99, zirconium-93, calcium-41 are some of the interest in the mass spec world. So now I want to, talk a little bit about performance testing. And I know this is, baseball's in the United States versus soccer or football in the rest of the world, but this is my example, right? So laboratory control samples to me are like pee-wee baseball. They're very easy to do versus real world samples. And, when you actually test the laboratories, say, oh, I have all this capability, but when you actually test them, results are all over the world. They're just all over. So I want to show you some examples of what I'm talking about. So here's an example: uranium mass spec, some neat solutions, right? What I would consider laboratory control samples, very easy, just dilute nitric acid with, known amounts of uranium or plutonium in it. So, so in our MAPEP program, we send these out occasionally. And of course, uranium's been around for a long time. People's been measuring it. They do very well, okay, on these very neat solutions, okay? So keep that in mind. But then plutonium, when we, mess up the, or mix up the ratios a little bit, as you can see, so out of 6 laboratories that participated in this study, for example, 4 of them failed the plutonium-239 versus, 3 out of 5 people actually failed the plutonium-240, and that's for actually measuring, the concentrations at around 34 picograms per gram or 23 picograms per gram. The ratios, of course, in mass spec, comes back right, but to quantitate how much was there, just from these neat solutions, we had a little bit of problems. Remember the uranium, where everybody did very well for neat solutions. Well, what happens in soil, right? So everybody should know that, soil from around the world has around a picocurie, and I'm sorry, I don't know what that is in millibecquerels, but about a picocurie per gram of just natural uranium, right? And so we send out a soil that has a higher content of uranium in a zirconium matrix, if you will. And, just natural soil, about 30% of the soil, the uranium contained in soil is in a zirconium type of a lattice. And so it's hard to dissolve, right? And so the people that leach samples can't get all of that uranium out. And so, this affects really the mass spec world, because those are usually the methods that are being used, to determine uranium. So we, test that, and we actually put a little bit more of that uranium that's in the zirconium lattice in the soils. And what happens? So out of 45 laboratories that are actually measuring this U-238, okay, only 27 laboratories actually reported zeros or statistical zeros, which is just befuddles me. It's kind of weird, because everybody that's doing radiological measurements ought to know that there's plutonium or uranium in soil, right? And so why would you report a zero? I'm not magic. I can't take uranium out of soil. So anyway, but as you can see on this chart, right? So dissolution by fusion, of course, then the laboratories are doing okay. Gamma spec wise, a little slightly low biased, but then the folks that are leaching, are severely biased low, 50 to 60% low. And then, the other half of the laboratories aren't even shown on this because they're reporting zeros. Other things that we see in performance testing for some of the mass spec standards that have been asked for, by both John and Dr. Lin is like radium, for example, right? So flow back water from crude oil exploration. Usually this is done by gamma spec, and of course the radium's usually measured through the radon daughter, or all the radon daughters, right? And so the 3-day radon escapes, and so you're always usually biased low in a performance testing type of sample. But then if you look at the radium-228 from the thorium series, just look at this part of the graph, and you can see that, they're doing okay. There was a couple laboratories that were just having problems. So now let me switch gears a little bit and just show you some of the kind of reference materials that we actually, take these isotopic standards that will incorporate into different reference materials, okay? So like I was saying earlier, the food products, for example, right? This is milk, eggs, chicken, beef, strawberries, blueberries. If you dehydrate those, you can actually, essentially just keep these shelf stable. Just, if you cap the samples and keep it just at regular room temperature, you don't get any molding or anything weird going on with your food stuff. So, keep this in mind as you're making reference materials. Dehydration is the way to go. And it's very easy because most foods are about 90% water. So, you know what the correction factor is to get back to the real result, right? Other things that we make, I think Dr. Lin, we actually made these for you guys. Here's some sausages. Here's some Vienna sausages, me making some Vienna sausages, poking little holes with the drill bit in them. And then we spike the sausage. And then I take some of that meat, plug up the hole, and, it looks just exactly like a little sausage. Some other interesting stuff is, chicken nuggets. Of course, milk, those places around reactors, of course, usually you have some kind of monitoring program for strontium and cesium in milks, nasal swabs. This is my favorite, the cement that we make. This is a 10-gram plug, and we make it homogeneous enough that you can take 10 milligrams out of this 10-gram plug, and it's statistically identical to within 3% of any other 10 milligrams within that sample. This is just showing some bottles of some soils at the very bottom of them that we had made some aged mixed fission products. If you're a radiation worker and you become highly contaminated and you want to donate your body to science, the United States Transuranic Registry will be happy to take you after you pass away and dissolve you up. Okay. And so before they go on to, regime of analysis for different things for models they're trying to make, we will make them some reference materials so that they can make sure and validate their methods. Here's one, there's a liver, for example, where, we dehydrate it. I put some refractory type of plutoniums in it, and then they can take the liver powder and do what they need. Bone ash, that's another one. And of course, all other, just all kinds of stuff. Of course, all kinds of soils. This is some wheat seeds. This is a good one. Asphalt, for example. How do you get a liquid isotope into a, a real thick, vicious oil? That was a good one. This is some of our synthetic fecal material. And then, of course, urine. We also make synthetic urine. I always put this slide up because my old boss would always tease me and say, "Guy, you can't pour piss out of a boot." So I always put this up and say, well, yeah, but I can pour it out of a graduated cylinder. So that's some radiobioassay jokes, right? Other things we make, these are called bottle mannequin absorbers or whole body phantoms. We make polyurethane lungs with any kind of radionuclides you want in them that's homogeneously distributed, tissue equivalent, of course. Thyroids, this is the ANSI thyroid neck phantom for radioiodines. It's a little 30-gram bottle that you fill up with radioiodine. And now, so those were just some of the, just various things we make. We make all kinds of stuff. And we're very good at what we do, but we're only as good as that initial reference material, the standards that we're using to incorporate into these real world standards. And hence, that's why I really need the NMIs, to start helping me out for these minor constituents that usually we had called contaminants, which, I no longer call contaminants, but they're just the minor constituents because we actually use them, when we're adding stuff together. Just some real world examples of stuff that's going on in the United States, at least from the Department of Energy. So Amchitka Islands is off the tip of Alaska. There was a lot of nuclear testing going on there in the 50s. They're trying to move the indigenous people back. And of course, so we're monitoring low levels of plutonium and uranium. And, on the picogram level, of course, fish, bone, kelp, that's kind of things that's being monitored so that, the indigenous people that are moving back onto these islands, making sure their food supplies safe. Of course, the Marshall Islands, this is the Bikini Atoll. Again, people are starting to move back to those islands. And so we actually have programs where we do whole body counting and urine monitoring and looking for plutonium, uranium, cesium, strontium, those kind of things. I think I'm running out of time. So just other things that happen, so when you have a school, next to a fuel reprocessing plant and, they discover, really low levels of, different isotopes, for example, U-235, neptunium, Tech-99, that's kind of drifted on the dust through the airs and gets stuck in the attic of the school. What happens? Well, the government ends up having to buy the school or, and build them new schools for the public, even though you don't really have a public health issue, because the amounts are so low, because our instrumentation has gotten so good, but it doesn't matter. I think the general public, you know, one atom of man-made radionuclides is probably too much, right? And my last thing that I just want to say is, you know, here at Russell, we single-handedly saved every man, woman, and child in India. And this is why, right? Because we have these people that, you know, will go find the weird stories from the 50s. In this case, some guys found out that the CIA was putting up a radiological generator, or, you know, an RTG, plutonium RTG, up in the Himalayas in the 50s when we were going to listen to, you know, some of the communications in China or something. And excuse me, as they were putting up the generator, you know, a snowstorm comes, they had to get off the mountain, but they left the generator up there. Of course, there was an avalanche and they lost the generator. So now at the headwaters of the Ganges River, you could possibly be contaminating that river with plutonium-238, which then they take water samples, have a laboratory that wasn't qualified to analyze it, and they say there's plutonium in that water, which then we were able to get a hold of those samples and, you know, show that there's actually not plutonium-238. So anyway, so these are some of the kind of things that I deal with in my day-to-day life here at Russell, and I'm happy to take any questions. Thank you.